All right, when we talked on Friday about magnitude and direction angle, we gave you an easier version of finding it than what the book does. All right, we used a tangent instead of having to find the magnitude and then using that to help you find a unit vector and using your cosine and all of that. So, how do we find the magnitude? Basically a distance formula, yep. Remember our symbol for it looks like that, okay? Magnitude of a vector is the first component squared plus the second component squared, and then you square root that sum. So in our case, we have the square root of -2 squared plus 5 squared, which gives us square root of 29 for a magnitude. Okay, so if you look in your book at how to find the direction angle, they're going to use magnitude to help you figure that out. Okay, they're using that idea that your components of a vector are the magnitude times the cosine of the direction angle and the magnitude times the sine of the direction angle. But we said that there's an easier way to find direction angle, and that's just to use tangent, because tangent takes the vertical component divided by the horizontal component, so b divided by a, right? And you don't have to worry about the magnitudes because they cancel each other out. So we said we could find the direction angle by just taking b over a. So in our particular case, we said we've got a 5 and a -2. Yes? So how do we find theta? Inverse tangent of -5/2. Yes? Okay. Go ahead and what did you get on your calculator for that? Okay, it came out as -68.199. All right, now I want you to think about it. Remember when we were doing all of our unit circle stuff, a negative angle means we're going from here in a negative direction, right? So they're saying that this direction angle is really as if we went down in a negative direction, 68, roughly 0.2 degrees, okay? But where is your vector? What quadrant is your vector in? If we have a vector, what was it, -2, 5? What quadrant are we in? We're in quadrant 2. Our vector is over here, yes? -2, 5. So when they give us that -68.199, you have to think of that as a reference angle. And if we have a 68-degree angle here, we also have the same reference angle here from your vector to the closest x-axis. So if this is 68.19 degrees, the direction of our vector is actually that angle. Okay, from the positive x-axis, how far do we turn in a positive direction to get to our vector? So what are we going to have to do to find the green one? Okay. Which gives us what? 0.801. Okay, so the magnitude of our vector is the square root of 29, and its direction is an angle of 111.8 degrees. We okay with that? Okay. You may want to revisit the last couple questions from your homework. If you just relied on the answer key that I put in Schoology, that was going with the books method. All right, we made it a little easier here using tangent. Don't just be writing stuff down because you see it on my answer key and not understanding where it's coming from. Okay. All right, the last little bit that we have for section 6.1 deals with some applications of vectors. First statement here, it says the velocity of a moving object is a vector because velocity has both magnitude and direction. We refer to the magnitude as the speed. Okay, so when we talk about a vector representing velocity, The length of the vector is an indication of the speed that whatever the object is moving at. Okay? All right. First question. It says a DC-10 jet aircraft is flying on a bearing of 65 degrees at 500 miles per hour. Find the component form of the velocity of the airplane. Recall that the bearing is the angle that the line of travel makes with due north, measured clockwise. So, bearing, direction angle, reference angle, those are different things. Yes? If we're going to write the component form of our vector, we need the magnitude of the vector times the cosine of the direction angle and the magnitude of the vector times the sine of the direction angle. Yes? Okay. So the first thing to do is, what is the direction angle? If it says we are heading at a bearing of 65 degrees, that means from due north, we've turned 65 degrees clockwise. Okay, that's how bearing is listed. But direction angle is from the positive x-axis going to our vector. Okay, so our direction angle in this case is only 25 degrees. It's not the 65-degree bearing that they gave me. Does that make sense? Okay. What is the magnitude? What's your magnitude for this one? .500 miles per hour, yes? When they give you a speed, that's your magnitude. So magnitude is 500. Okay, so we are going to say our vector has two components. The first component would be the magnitude, 500, times what? Cosine of 25 degrees, and then the second component is 500 times the sine of 25 degrees. All right, go ahead and grab your calculators. Let's get some decimals for those. All right, agree, disagree with those two values? Okay, so what that means when we talk about breaking a vector into its components, this is your horizontal component, right? This is your vertical component. So when we say that we're flying this plane at 500 miles per hour at a bearing of 65 degrees or a direction angle of 25 degrees, we're really saying that plane is moving in a horizontal direction, okay, 453 miles per hour, and in a vertical direction, about 211 miles per hour. Does that make sense? We're just breaking it into the two components. The result is that we are flying at a bearing of 65 going 500. Okay? Questions on that? All right. Example 8. It's going to be the most involved of the four that we're doing today. It says pilot Megan McCarty's flight plan has her leaving San Francisco International Airport and flying a Boeing 727 due east. There is a 65 mile per hour wind with a bearing of 60 degrees. Find the compass heading or the bearing that she should follow and determine what the airplane's ground speed will be, assuming that its speed with no wind is 450 miles per hour. Okay, we need to break this down. The airplane she wants to fly due east. Yes? But there is a wind at 65 miles per hour that's pushing her off course. Okay? So if she actually heads due east, that wind is going to push her up into quadrant 1. So in order to have the result being that she's heading due east, she's actually going to have to fly a little southeast, yes, in order for that wind to push her back to where she wants to be. Okay? So this is a case of adding two vectors. You're adding the plane where she's actually flying with the wind to get vector AD. Okay? So vector AD is really vector AC plus vector AB. Okay? The plane plus the wind is going to give you your resulting speed and direction. So we need to come up with component forms for vector AC and vector AB. And then we can add them together to get AD. Does that make sense? Okay. They've asked us for two things. They want us to figure out what bearing she needs to fly at. So we're looking for the bearing of vector AB. Where should she actually head so that the wind pushes her so she's flying due east? And then they also said determine the airplane's ground speed. So how fast is she actually flying? How fast is that plane going? Without wind, it's going 450 miles per hour, but the wind is going to help. All right, it's going to go faster. So we need the speed or magnitude of AD. Okay. Questions so far? Does the picture make sense? Yes, no, some indication would be helpful. Okay. So let's look at if we can come up with some components for AC and AB. AC is the wind, right? And it said it has a bearing of 60 degrees. So what is the direction angle for that wind? Everybody okay with that, that it's 30 degrees? Its bearing is 60. The direction angle here would be 30 degrees. Okay, so the components for this is going to be its magnitude. Well, how fast is the wind going? Okay, so speed is magnitude. So we have 65 cosine of its direction angle, which is 30 degrees, and 65 sine of 30 degrees. We good with that? Okay, those are going to give us some decimals. Let's just wait till the end to actually put it in our calculator. Okay. Let's look at vector AB. Now, we are given a magnitude for AB. What do they tell us? 450 degrees, or 450 miles per hour, right? But they haven't given us the direction angle. We have to find that. So we're going to just set it up as 450 cosine theta and 450 sine theta. We good with that? All right. And we said the resulting vector AD is just those two added together. Okay, so my components for this resulting vector is going to be the first component plus the first component, right? We add those. So we have 65 cosine 30 degrees plus 450 cosine theta. And then if we add the second components, we have 65 sine 30 degrees plus 450 sine theta. Okay? We good so far? Okay. What do we know about vector AD other than it's going 450 miles per hour? It's what? we're flying due east, right? Yes? So there is a horizontal component here, but there is no vertical component. Does that make sense? So can we substitute in and say that we know we're going to have a horizontal component, but this vertical component should come out to be 0. If we're heading due east, there is no vertical movement. So can we take and set this equal to 0? That's going to help us figure out what that theta should be. Okay? So we've got 65 sine 30 plus 450 sine theta, and it should equal 0. Okay? How would we solve that? We need to get sine theta by itself. What do? Subtract 65 sine 30. We okay with that? Okay, can we then divide out the 450? So we're going to end up with the sine of theta is negative 65 sine 30 degrees divided by 450. Did everybody follow what I did there? Okay, and then how do we find theta? Okay, so grab your calculators. You need to do the inverse sine of negative 65 sine 30 divided by 450. Double check that your calculator is in degree mode. Well, we don't know enough about the horizontal component to use that piece. We only know that the vertical component is 0. Okay? You should get a small negative number, negative 4.142. Okay, so let's go back to our picture. What we're saying is that she's going to fly in this direction with an angle here of negative about 4 degrees. So she's flying a little bit south of that due east so that the wind will push her up. We okay with that? So what would the bearing be? Remember, bearing is from due north. So how far are we from due north all the way to there? 94.142 degrees. Yes? So we've answered the first question. We've found the bearing that she should head at. Okay. The second question is they want us to figure out the magnitude or the speed of vector AD, the resulting vector. Okay, so let's go back to what we had for vector AD. Okay, we had this. Yes? That was our vector. So we have the magnitude of AD. We have to take the square root of the first component squared plus the second component squared. Okay, so first component is 65 cosine 30 plus 450. All right, let's try this again. Cosine 30 plus 450 cosine of negative 4.142. Okay, what's the second component? It's 0. Okay, so what's really going to happen here? Adding 0 squared doesn't do anything, right? So I'm taking this whole big piece here and I'm squaring all of that, right? And then I'm square rooting it. So what's going to happen? It's going to cancel out except for one thing. If it was negative, we aren't going to see that, right? Because when you square something, it turns it positive. When you square with that positive, you just get a positive answer out. So go ahead and use your calculator. 65 cosine 30 plus 450 cosine negative 4.142. If it comes out negative, just drop the negative. What do we end up with? Okay, so she has to head at a bearing of 94, roughly 94 degrees, flying at 450 miles per hour. The wind is going to push her a little bit, so she's going to end up heading due east, all right, bearing 90 degrees. And she's going to be flying at, the plane is actually going to be going 505 miles per hour, all right, because the wind is pushing it a little bit. Questions on that one? All right. The next two are a lot shorter. Example 9, it says a force of 30 pounds just keeps the box in this picture from sliding down the ramp that's inclined at 20 degrees. We want to find the weight of the box. All right, so let's look at our picture. We have a ramp. Its incline is 20 degrees. We have this box. Look at vector AD. Okay, vector AD. If there was nothing holding that box up, right, it would just slide down. They're saying that if we have a 30-pound force, it'll keep it from moving, right? That means vector AD has to be 30, right? It's sliding down at 30 pounds. A 30-pound force would keep it from moving, going in the opposite direction. So vector AD has a magnitude of 30. Okay? Vector AB is the weight of the box, right? It's going straight down, perpendicular to the ground. Okay, so we're going to say the magnitude of vector AB is, they've just labeled it W for weight. Okay. Can I take this vector and move it down here? Right, we talked last week about just picking up a vector. We can move it anywhere in the coordinate plane. It's still the same vector, right? So BC is really the same as, CB is really the same as AD. Okay. Now, there's another angle that's been labeled 20 degrees, and I want you to think about why it is 20 degrees. If we think of this right triangle here, okay, 20-degree angle down here, what would this be? 70 degrees. And now look at this angle, right? We have a right angle there. So if we've used 70 degrees up where the W is listed there, what's this angle here? 20 degrees again. Okay, so that's where they're getting it labeled with a 20. Does that make sense? Okay, now I want you to look at this triangle. Okay, we're going to turn it a little bit just so it's easier to picture. Okay. So vector CB has a force of 30, magnitude of 30. We know that this angle is 20 degrees, and we are trying to find the hypotenuse of that, right? Vector AB, which is the weight. We okay with that? Do you see a trig function that we could use to find W? Think back to your SOHCAHTOA stuff. Sine? Okay, so we could say the sine of our 20-degree angle is what? 30 over W. Okay. Can we multiply the W to the left side and divide the sine of 20 down to the right? So W equals 30 divided by the sine of 20. Okay, grab your calculators. What do we end up with for weight? Okay. And weight was measured in pounds? Okay. Questions on that one? All right, last one. It says during one part of its migration, a salmon is swimming at 6 miles per hour and the current is flowing downstream at 3 miles per hour at an angle of 7 degrees. How fast is the salmon moving upstream? Okay, it's not the 6 miles per hour. That's how fast the salmon is actually trying to swim. But what's happening? The current is coming against it, right? So it's going to slow it down. So its resulting speed isn't going to be as fast. But if you look at our picture, we have the salmon swimming up here. Yes? The current is pushing it backwards and at a little bit of an angle. Okay? So the result is going to be vector CB. All right? It's going to be slowed down and it's going to be a little bit off of vertical. Does that make sense? Okay. So to find our vector CB, we have to add CA with AB. Okay, so kind of like the plain one, we've got to come up with component forms for our two vectors. So what do we know? Let's start with CA. What do we know about this vector? This is A up here. CA is going straight up, right? Due north? Okay, so if we picture our origin being here, its direction angle is 90. So its components would be the magnitude times the cosine of 90 and the magnitude times the sine of 90. What's the magnitude of that one? 6. The speed of the salmon without interest in still water was 6. So we have 6 cosine 90 and then 6 sine 90. But what is the cosine of 90 degrees? Think about our unit circle. What was the ordered pair at 90 degrees? 0, 1. So the cosine was 0 and the sine was 1. So the components for CA are really just 0, 6. Yes? There is no horizontal component because it's headed straight north, right? There's only a vertical component. We good with that? Okay, let's look at vector AB. Okay, this is the current. What do we know about that? It's going 3 miles per hour and, okay, now be careful here. The 7 degrees based on our picture is this theta here. Yes? But what is the direction angle? If this is our origin, how did we really go? 83 degrees in a negative direction? Okay, so this would be 3 cosine of negative 83 degrees and 3 sine of negative 83 degrees. Does that make sense? Okay. And what we want is the sum of those two vectors. We want vector CB. All right, this one here. So CB, we said, was just the sum of the other two. All right. So we have 0 plus 3 cosine of negative 83 degrees. And then we have 6 plus 3 sine of negative 83 degrees. Let's go ahead and get some decimals for those. All right, glancing at some papers, I'm seeing those too. Are we getting those same ones? Yes? Okay. Now, the question was, how fast is the salmon really moving upstream? So we need the magnitude of this vector. So we're going to take 0.366 and square it. We're going to take 3.022 and square it, add them together, square root it all. All right, seeing 3.044 miles per hour. Okay. Now, is that reasonable? The salmon was swimming 6 miles up. The current was pushing it back 3 miles per hour, a little off course, right? Not straight back. If it was straight back, right, it would be just an even 3 miles per hour result. But got a little extra because it was a little bit off of vertical. So 3.044 miles per hour. You okay with that? All right. You guys are going to work on day 2. Remember that you're also working on those final review packets. Okay, the blue one should be done tomorrow. The white one you should be working on, so it's done the next day.